Okay, as long as we're talking about stress and strain, there's one more thing I'd like to talk about. I'd like to talk about how you can control the strength of a material by designing it, by controlling the size of the grains that make up the material. Okay? Just to illustrate, this spoon, which we bent, this is made of metal, and the metal is made up of metal atoms, of course. And you might think they're completely disordered, but actually they're in the form of crystals, but small crystallites which are jammed together. Each crystallite is called a grain, and the size of the crystallites is the grain size. And that turns out to control some of the properties of the metal. Normally, metals are ductile. They have a low yield strength. And that means that I can easily bend this, as we saw a moment ago. Okay? And that's great for some applications, but for some applications, it's not great. We don't want the edge of a knife to be ductile, for example. We want it to be hard. Okay? And let's see how we might be able to engineer such a thing. If you'll hang on for a second. Okay, so as I mentioned, metals are usually soft and ductile. And the reason that they're ductile is that planes of atoms in the material can easily slide over one another in response to a force. So if I apply a shear force to this metal, pulling on part of it, pushing on another, I can get the planes of atoms to slide against each other. And that's plastic deformation. Okay? In fact, if we look more closely at how this works, we can see something, we can see just how easy this is. Hang on. All right. This is a more realistic picture of how the metal fails, how the planes of atoms slide over one another. And what's interesting is that you don't actually have to do it all at once. Instead, this actually happens by displacing one row of atom at a time. So we start with something called a dislocation, a defect in the crystal where perhaps there's a missing row of atoms. Okay? Then when I apply a force, all that has to happen is that the bonds connecting these atoms to those atoms have to flip over. And that allows that particular row of atoms to move forward. Now my dislocation, my defect, has moved forward by one atomic unit. And now I can keep doing that, flip, 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 until finally I get to the edge of the material. And now the entire upper plane of atoms has moved over by one step. That's important because it takes much less force to do this than it would to actually move all the atoms at the same time. And the fact that this can happen is what makes metals so ductile, so soft. Okay? So the material fails to dislocation due to dislocation, which propagates through the material when we apply a force. Now, what I mentioned is this. When I look at a piece of material, what looks like a solid piece of metal is actually composed of different grains, different small pieces. Here, a piece of aluminum that's been treated so that we can see the grain boundaries. All right? This is an electron microscope picture. We're looking at a very small scale. Here's one grain here. Here's another grain as well. If I look at an atomic resolution electron microscope picture, I can see all of the atoms at a grain boundary. Here's one part in one grain. Here's the part in the other grain. And you can see that at the boundary, the two are just jammed together. And so the nice crystalline order that I have above and below kind of falls apart right at the grain boundary. Well, the important thing about this for our discussion is that these dislocations, they get trapped at a grain boundary. Actually, they sort of dissipate. They can't move through a grain boundary. So that means when I apply a force, I can only have dislocation motion over a very small range, and then it gets stopped or pinned. And the result of that is that due to grain boundaries, the material becomes less ductile and more brittle. Here's some data. I think this is from our book. These are 3 different nanostructured materials. One that has relatively large grains. The grains are maybe 10 microns on a side. Next one that has smaller grains. And then finally, a nanoscale material where the grains are only a few nanometers on a side. So this is an atomic resolution TEM. You can pick out the planes of atoms in this grain, and you can see the scale bar over here. The stress-strain graph below shows the different properties of these materials. Here's A, the large-grained material. Here's C, the small-grained material. Okay? Notice that they all have the same elastic constant, but A reaches plastic deformation at a much lower stress, because at this stress, I can get the propagation of dislocations through the material, and the whole material can deform. Then there's a rather wide region over which, I get plastic deformation, okay? This is showing us that the material is ductile, and then finally it fails. On the other hand, material B, or even material C, are much more brittle. The smallest one, material D, I guess this one has grains that are only 30 nanometers wide. You see that, first of all, the yield stress is much higher. The material is much harder, okay? But once we reach the yield stress, either we have a small region of plastic deformation, or here, none at all. Once we reach the yield stress for material D, it simply snaps, it simply breaks. So I have a hard, brittle material, material D, or a soft, ductile material, or whatever I like in between, just by engineering the grain size in the material. And notice, to get the hardest material, material D, I have to make the grains nanoscale. They have to be nanometer sized. Okay, let's stop here.